So today's presentation is about the non-contact MEMS sensor array inspection of composites and metallic parts using lamp waves, and our speaker is Arno Volker. This event is also co-organized and published also by our other chapters, let's say, so local chapter Aberdeen, London, Paris, Czech Republic, Netherlands, Stavanger, and DGMK, which is a German company. So if you have a question, Arno likes it also. If you want, you can just also interrupt. So then in this case, just raise your hand and then Jan will unmute you, or you just write your question in the chat, and then we can also read it for you, or you can ask it after the presentation, whatever you like. So with that, I will hand the floor to Arno, who will introduce himself and let us know what his presentation today will be about.
Well, thank you, Hannes. A little bit about my background. My name is Arno Volker. I work at TNO. I'm in fact a colleague of Hannes. We both work in the acoustics and sonar. It used to be acoustics and sonar, now it has changed. But my background, I hold a master's degree from TU Delft in physics and a PhD in geophysics. During my PhD, I used to look at the influence of the seismic data acquisition geometry on imaging. And at that time, part of my work involved, there's the cat.
Thanks.
Yeah, that's the risky part of working from home. A part of my work involved scaled seismic experiments to collect 3D data, because at that time, which is now more than 20 years ago, 3D modeling was still quite challenging, and what we then did is build scale models and performed ultrasonic measurements. So after finishing my PhD, I continued working in ultrasonics, and then I focused on using ultrasound for industrial inspection, and this is also where this talk will be about. But what you will see is that there are a lot of similarities between the ultrasonic work that we do and seismic data acquisition and processing. So hopefully you will enjoy this presentation. Now share my screen, and hopefully you can see my presentation. Is it visible, Hans?
Yes, it's nice. Only if you can change the display settings that we see the presentation.
Okay, yeah. It always switches to the wrong screen.
Great, thanks.
Okay, so first a little bit of background. The work that we're doing is now mainly focused on the aerospace industry, and companies that produce aircraft basically produce large skin parts for the fuselage or wings. And of course, these are all safety critical components of an aircraft. So 100% inspection is required before the part can be integrated into a full aircraft. So essentially, there are two approaches in inspecting these parts. You can send ultrasound through a part from one side to the other, and then basically, if there's an imperfection, you'll see a drop in amplitude, which is the main mechanism of detection. Alternatively, you could put a sensor on the part itself and use a working pulse echo, and then again, imperfections in the part will change the echo pattern, and then that's the main approach. Now here you see a few pictures from a system that basically no longer exists, but used to be at Fokker in Papendrecht, where they were building parts in that time for the A380, so the big Airbus aircraft. And as I said, they need to inspect that, and the way that they did that was using a squirter system, which basically consists of two nozzles from which a water jet emerges, and through this water jet, ultrasound is transmitted from one side to the other. And they have a huge scanning system where they have parts like this, and they would scan the whole thing. To give you an idea, basically, the vertical dimensions are typically something like 4 meters, and in horizontal direction, it's about 8 meters. And they would inspect that with a grid of 2 to 3 millimeter by moving the water jets over the part. Initially, they had in mind that they could use 4 water jets to speed up the inspection, but you can already see from this picture there's a lot of splash. And what happens is, if you have 4 water jets, droplets from one jet will fall through the other one, and that causes a lot of noise in the image. So in the end, it only turned out to be possible to measure with 1 or 2 water jets. And then typically you'd get images looking like this, where basically it's a grayscale image where you see the geometrical features in the parts, and also where defects show up. Basically, both methods in inspecting, both in transmission or impulse echo, require water coupling. When the parts are curved, of course, it has to be an aircraft in the end, so it's always a bit curved. Alignment of both probes is important. One of the most important limitations is this type of an inspection is generally slow. At that time, they were scanning more than 8 hours on this size of a part before the measurement was finished, and then they need to do an interpretation. The type of defects that they were after, there's a variety. Inclusions, that could be tape residue that ends up in the part, and delaminations. At that time they were using glare, and glare is a layered material of alternating layers of aluminum and a fiber reinforced resin. And of course, you could have disbonds between these layers or delaminations. Other type of defects are voids and porosity. And porosity is basically a cluster of small gas bubbles that remains in the part. And here I have a couple of images how these type of defects show up. So here you see an area with a darker area, which indicates that there's more attenuation, which is in this case caused by porosity. Here, for example, there's a small debond. 2 layers didn't adhere to each other, blocking the transmission of sound. Here there's a bit of tape included, and here a whole layer of prepreg is folded, which is a quite dramatic type of defect. So at that time, the method, of course, did perform as required. Otherwise, it wouldn't have been used for this application. But in the end, it was very slow and challenging. So generally speaking, if you now look at the trends in the aerospace industry, companies are starting to use more and more carbon fiber, but also metal bonded panels. So this is thin layers of aluminum bonded together. are still frequently being used to produce aircraft. So basically, the parts that they now build are either fiber reinforced or carbon fiber reinforced materials or metal bonded panels, and both need to be cured in an autoclave. And to minimize energy consumption, there's a tendency that parts are built in one go instead of in several steps, which means that a part normally consists of a skin with so-called stringers to stiffen the structure, because let's say the skin is generally very thin, and you need stiffness to make it a rigid part. Which means that in some cases, two-sided inspection no longer is possible because the stringer, which is on the inside, of course, of the skin, disturbs the ultrasound water jet. So these techniques can no longer be used then. As I said, inspections are slow, and there's a tendency to build more aircraft in a shorter amount of time. And some parts have no non-parallel surfaces, which also means that inspection with conventional approaches is difficult. And there is a variety of reasons why you don't like water. First of all, some parts absorb a little bit of water, which require drying afterwards. But also the systems that are deployed tend to corrode with all this water. So there's a variety of reasons that you don't want to use water. And preferably, you want to minimize the interpretation of your inspection and make it easier, such that you don't need very high qualified people to perform the analysis. So we came up with a different approach, and that will be the main part of my my presentation. I'll start with a small anecdote. At some point at TNO, we were working on haptic feedback with ultrasound. The idea was that you could generate such a high sound pressure in air that you, in fact, could feel it with your hands, or you could levitate small particles in air made from polystyrene, for example. And I was making a movie with my mobile phone at that time because it was quite amusing to see. And at some point, I realized that my microphone was picking up the ultrasound and caused all kind of noise in the recording. And then just a colleague of mine who recently joined TNO came from a hearing aid company, and he explained to me that these microphones that are in your mobile phone or in a hearing aid, if you have one, are in fact sensitive to pick up ultrasound, and for people who use hearing aids, ultrasound can be a nuisance because you could hear it. And that triggered an idea in my head, because I remembered all the fun that we had with the water jets, but this gave us an opportunity to get rid of the water jet and use an alternative approach. So the concept is basically that you fill the part for inspection with lamp waves, which are low frequency, in this case, flexural waves that propagate through the part. And because the motion, the wave motion is such that these waves have a strong normal component, they tend to radiate in air, which you can pick up with this MEMS array. So what you see on the slide here is a picture of these MEMS sensors, where this small opening is in fact called the sound port, where the sound enters the sensor. And what we did is we integrated these sensors on a flex print with some amplifiers behind it, and created small arrays of 32 elements sitting next to each other, And in the end, we made 4 modules of 32 elements to create an array. The pitch of the array is about 3 millimeters, so this total length is about 40 centimeters, to give you an idea. And you could mount this array, for example, on a robotic arm. I have a small video here. Hopefully it plays. Here you see an overview picture where there's, in this case, a glare part. Hopefully you can see the coaxial wire connecting a piezoelectric element sitting underneath, which generates waves in the panel. And the array is scanned over the part and records the wave field. To give you an idea, the distance between surface and array in this case is about 10 centimeters. And if you look at the wave field that you measure, then basically it looks like a seismic wave field. Here you see the wave field as it's being measured by the MEMS array. I will let it run again, or let it run a couple of times. One of the features of this type of waves is that they are dispersive, and the phase velocity depends on the thickness. And here, for example, if you look carefully, you see some diffractions because of the defects that are present. Now, of course, I guess the people online are familiar looking at these type of images and can appreciate it, but most people working in non-destructive testing, for them it's much too complicated, and you need to present the information in another way. And that's what we do, is we translate this wave field into a thickness map, where basically defects show up as local thinning. And in this example, we had 4 layers of glare with varying thickness, and embedded are artificial defects, where the smallest size here is 3 millimeter, and the largest ones are 12 millimeter. And as I said, the basic principle of this approach is that the lamp wave velocity depends on the local thickness, and we measure the local phase velocity by a bandpass filtering approach in the wave number frequency domain to basically determine the phase velocity at any xy point, and then making use of a dispersion curve, you can map that into a thickness. If you look at the main parts that we need for an inspection, it's similar to a seismic experiment. We have a piezo actuator, which is a piezo stack applying a normal vibration to the surface, like a vibrosaur, and that causes these bending lamp waves to emerge. And the wave motion is basically like this. So it's a flexural wave which radiates in air, which you see from the animation here. But the thing is that the phase velocity of these waves is frequency dependent. So also the refraction angle in air is frequency dependent. And in order to measure the phase velocity in this plane, you need to backpropagate the waves back to the surface, which will automatically take care of the differences in refraction angle. And after backpropagation, we analyze the wave field at the surface. And then in the end, making use of this dispersion curve, we present a thickness map, where, as I said, the defects show up as local thinning in the part. This method can be applied both on metallic parts and composite parts. And the phase velocity, of course, depends on the material properties and thickness. And for fiber composite parts, it's slightly more complicated because there the fiber orientation adds anisotropy, making the wave propagation slightly more complicated. A little bit more on the components that we need. Apart from the MEMS sensor array that records the wave field, we use laser profilers to measure the shape of the surface. As already said, most parts on an aircraft are not flat, but have some curvature. And in order to properly propagate the wave field to the surface, we need to measure the curvature of the wave field. Then we have this actuator, and that can be attached using a vacuum source to the surface, such that you can also mount it upside down on an aircraft wing, for example. And we look at the variety of different systems to inspect the part. You could use an XY scanner or a robot or a smaller version called a cobot to move the sensor head, which is basically the MEMS array plus laser profilers over the part. And we have a 128 channel digitizer that records the wave field. As I said, we can basically perform the measurement at a very large standoff, typically in the order of 100 millimeter or more. That's an advantage because you want to avoid collision of the sensor head with the part. So then a little bit more standoff makes it easier to avoid collisions. There's a variety of shapes that we can measure. Planar panels, single and double curved panels, provided that curvature compared to the wavelength is not too strong, because then you run into all kind of practical challenges. Alternatively, if you have large parts, you could also apply a contour following approach instead of performing a scan on the planar surface. We prefer a planar acquisition surface because then the back propagation is easily done in the wave number frequency domain. And then this basically gives a little bit of information about the data processing steps that we follow. These MEMS sensors are not identical, so we require to perform a calibration, which basically is a sideways scan where each sensor passes over the same position on the surface, which means that then you know that the waveform that you record should be identical for all sensors, and then it's quite straightforward to design a filter that corrects for these differences. Then we need to backpropagate the wavefield to the surface, as I already explained. That takes care of the frequency dependence of the refraction angle and allows you to basically measure the in-plane phase velocity, which is done by an algorithm that we call direct velocity mapping, which is a kind of a band pass filtering approach in the frequency domain where you search for the wave number with the maximum amplitude at a given XY location, and from this wave number you calculate the phase velocity. Once you have that, you basically the whole procedure is repeated for a whole range of frequencies. Using a single frequency, you get a kind of noisy image, and if you apply this for a range of frequencies, then you can average out the noise and you get a nice sharp image. So typically the frequency range that we deploy is from 40 to 150 kilohertz. And then the mapping of phase velocity back to thickness is quite simple. You have a dispersion curve relating phase velocity and thickness for a given frequency, and then basically, it's a simple mapping to obtain the thickness for a given XY location. And as I said, you do that for all the frequencies, and then you stack, which gives you one thickness reading for a given XY location. In principle, we need to be able to detect the same type of defects as conventional techniques. And it turns out that basically all relevant defects have an effect of the phase velocity of the lamp wave. The effect of porosity on the phase velocity of lamp waves is modest, to put it mildly. So that's a bit more challenging. But all other type of defects have a significant effect on the phase velocity. Apart from that, there's a resolution requirement. Depending on how critical the part is, you need to be able to detect defects of either 6 millimeter or 10 millimeter in diameter. And if you look at the resolution test, basically with this approach, you can in fact detect 6 millimeter defects. The sizing at which depth this defect occurs, gets a little bit less with smaller diameters. So that's why we make a distinction between properly sized in terms of depth and detected. But in fact, we can detect all defects, and that's basically illustrated here in this panel, where we created small defects of about 3 millimeter, 6 and 12 millimeter defects. And the 6 and 12 millimeter defects are properly detected. And we can basically measure the local thickness and the depth at which these defects occur. Here I have an example where we make a comparison between conventional ultrasonic inspection techniques and our new approach. Two different samples. Here's one sample with embedded defects and foam dots on the outside. Of course, we did our measurements on the opposite side of the foam dots so that they wouldn't affect the sound leaving the part. And that's why we don't see them, but we do see the embedded defects. And if you look carefully, all defects show up in both images. What happens here is that we had a piezo element mounted on the same side as the MEMS array, and then it turned out that in fact we were also generating waves through the coaxial cable that connected the piezoelectric element, which from an acoustic perspective might be interesting, but practically you don't want to see this. So in the future we will have the sensor on the opposite side, or the actuator on the opposite side of the sensor array. Another part that we created is this one, where we have several thicknesses and different types of defects embedded. There were some gaps between the layers of aluminum that are imaged here, and the defect that I particularly like is this one. This one is the image that we create with the lamp waves, and this is the image that we created using a 5 megahertz ultrasonic transmission scan. And you see that the morphology of the defect looks very similar, which shows a little bit of information about the resolution that you can obtain with this approach. As I already mentioned, more and more aircrafts are now made from carbon fiber instead of aluminum. And normally, what is done is that these carbon fibers are laid up in a certain sequence, and that's basically represented in this way. So here the fiber layer was plus 45 degrees, minus 45, 90, plus 45, 0, minus 45, and then S stands for symmetric. So you have a similar sequence, but then symmetric around the neutral line of the part. And because of this fiber orientation, the material becomes anisotropic, meaning that the phase velocity in plane depends on the direction of propagation. And we need to take that into account to properly map the measured phase velocity back to thickness. And here's an example where we ran a finite difference model with this layup and compared that to the actual measurement. So the black curves, which coincide with the color curves, are the results obtained from the finite difference modeling, and the color curves are the results that we obtained from measurements on this plate. And we did measurements on both sides, so in a convex and concave orientation, the panel was measured, and that produces similar images as you can see in this picture. Then we took one step further, and we basically measured half of a fuselage of a single aisle aircraft, which was at a lab from the TU Delft in Delft. What you see here is basically the opening of a cargo door and the part of the opening of a passenger door. And the color here represents the thickness / fiber layup that was in this component. We measured in 3 different areas, labeled A, B, and C. And at that time, we had to place our scanning system on a small card that we could put in the fuselage. The whole thing has a diameter of 4 meters and a length of about 8 meters. So it's a fairly big component. Here's some pictures of the wave field as function of time. So the actuator is sitting somewhere here, and you see the wavefront propagating through the part. Here, what you see is the area near the cargo door, somewhere here, and then at some point there's a stepwise change in thickness. So you see the wavelength increasing because at a larger thickness, these waves tend to travel faster. And there's the influence of the curvature of the part, which means that the angle at which the wave field arrives at the sensor array also changes, and then it also has influence of gives an appearance of an increasing wavelength. And if you apply the data processing, then typically these are the images that you obtain. Here is a kind of uniform thickness, but with one part significantly thicker, and then this light blue thin component that you see here. Here at the cargo door, you see a stepwise change in thickness, and you see also the fiber orientation in the images. And yeah, there's also some structure here, which is basically this stepwise structure that you see here. In these parts, we didn't see any defects. But here are some examples where there are, in fact, defects in the parts. Both metal. These are both metal parts and fiber composite parts. This is a metallic panel where here there's a small delamination of basically this stiffener, where at one side the adhesive there's a disbond of the adhesive part. Now what you see is that because we measure from one side, normally the smooth side, we can basically see all features, while if you measure in transmission as a comparison, then in this area where basically you have this so-called omega stringer, yeah, there's a whole lot of air in between here, which means that you cannot detect anything there. And in fact, in the bond line, there's a small channel present, which you wouldn't detect with this conventional approach. And with our concept, you basically see a small channel running from one side to the other. Another example of a bond line or weld inspection is this composite part. This is basically melted together, and yeah, at some point it didn't properly attach to each other. So here you see some welding defects. And you also see that in this corner the part is slightly thinner, which you can also see in this picture maybe. So it's only a small amount, but we can image this. So far, only talked about inspection for quality assurance, but one other application of this technology is in-service inspection. And for in-service inspection, basically there are two applications. Nowadays, still most aircraft are made of aluminum, and similar to steel, aluminum can corrode, which needs to be detected. And when it's detected, the corrosion is milled away, and then the remaining wall thickness needs to be measured. And here's an example how that could look like in a hangar. Again, here's the actuator, and here's the MEMS array. And here's a picture of a wing flap from a real aircraft. The aircraft had a small incident. An APU crashed into it at the airport, creating a dent. So that's why they gave it to us, because it could no longer fly. But it's a very useful part for testing this approach. What you see here, hopefully, is that there are rows of rivets. Basically, we can image the individual rivets in the part, and we can also see the substructure in there. There's a bracket here that runs all the way through, holding the different parts of different pieces of aluminum together. Normally, what they do is that they use a kind of adhesive to bond the bracket to the surface, and then put rivets through it. And here the whole part detached, so you see much thinner, darker area where there's less acoustic energy coming from the part. And here you see that the brackets is still in place. This part is thicker because there is an attachment of that wing flap to the aircraft that needs more stiffness, and that's why it's thicker there. Another issue that you could have with composite aircraft is impact damage. And impact damage could come from a variety of sources. It could either be caused by heavy hail storms, but also by bird strikes, but also vehicles hitting the aircraft when it's parked at an airport. And the current approach of detecting that delamination is by tapping with a coin on the surface and then listening to the different sounds it makes. Similar, if you want to verify whether your tiles in your bathroom are still properly bonded to the wall, you could tap on it and you could hear the difference. Well, the similar approach is followed there. And with this technique, you quickly inspect parts and you can detect small defects. And here's an example of an impact damage. So typical practical implementation could be either, let's say, a robotic or cobot arm or a gantry where you mount the array and you could inspect the part from a very large standoff with a relatively high speed. We envision that with this technique, you can, in the end, inspect parts up to, let's say, a square meter per minute, while nowadays it's more like 1 to 2 square meters per hour. So it's a significant improvement in speed. The technique, of course, uses an actuator to generate sound waves. In the whole processing that we apply, we're not using the location of the actuator, which could mean that you can have multiple actuators operating at the same time in order to cover a large area, which is mainly useful for quality assurance, while for in-service inspection, you're generally not interested in inspecting the whole aircraft, but only in locations where you expect an incident might have happened. And with this technique, you can detect a variety of defects useful for corrosion, wall thickness mapping, and all type of production defects. And one more example here. People who build parts for aircraft always like to do impact testing and then drop heavy objects on a part and see what happens. This is also what was done here. And then in the end, the whole stiffener or half of the stiffener detached. And that's what you see in this image. So we're currently working on the development of this technique, which offers quite unique and interesting possibilities because these MEMS sensors are really low cost. Typically, we're talking about 50 cents per piece, which would allow you to, in the end, build large arrays and do very fast non-contact inspection of big components. In principle, we could inspect any shape, provided that the curvature is not that strong. And in the end, you get a thickness map from which you could detect defects by looking at changes in its thickness. And that basically also makes that the method is quite easy to understand, and interpretation of the images that are produced is not so complicated, which is definitely an advantage with, let's say, the fact that it becomes more and more difficult to acquire skilled and well-trained people. So with that, I thank you for your attention, and hopefully there are some questions that I can answer for you.
Yes, Arno, thank you very much. Very nice presentation, very interesting, and also very interesting applications and very useful, I think. So nice stuff. I see a couple of questions. I also asked some myself, so I don't know, but I will leave the floor to the others first. So I think Artem, he asked, Jan, if you want, you can unmute him. Or he asked, how many MEMS do you have in an array?
Currently, we're using 128 with a pitch of 3 millimeter. That is currently limited by the data acquisition system that we have, which is also 128 channels. But in principle, you could use much more. I realize that compared to seismic surveys, these numbers are still very small. But in principle, you could go to pretty large numbers.
Nice, but it's enough to apply array technology, right? So like stacking power, that kind of
So
things.
basically, what we do is we measure several swaths, so to say. So it's not one pass, but then the scanner moves to the side, and we take a next pass. So in the end, a typical data set consists of 3 or 4 swaths covering an area of 1 to 2 meter, 1 by 2 meter, basically.
Oh.
With the current system, but
Okay.
Our lab is limited in size, so.
Yeah, I know. By the way, to the people who have any questions, you can always just raise your hand and then Jan can unmute you, right? If you don't like to type. In the meanwhile, also Artem asked, what is the maximum thickness of the specimen? Let's say, what's the maximum you can do?
Yeah, basically, if you look at the dispersion curve, I'll go back to here. No. What happens is if you go to larger thickness, the dispersion curve tends to level off, which means that in thicker parts you're less sensitive than in thin parts. And at some point, the part is so thick that it becomes a Rayleigh wave instead of a lamp wave. But we did use these type of waves to inspect concrete, where we had a slab of let me think. I'm not sure whether it was 50 or 100 millimeter thick, but at least it was much thicker than this. But then the nature of the wave changes, and it becomes a Rayleigh wave instead of a lamp wave. For the applications that we're now working on, limitation is typically 8 to 10 millimeters.
I see. Nice. Also, you all can unmute yourself. By the way, I just saw from Jan.
I just unmuted myself. Peter Robotham here. So my question was about the portability of the system. The results you've shown are all from kind of inside, fairly quiet environments. What are the limitations for taking this out to the North Sea with wind and wave noise or whatever? Does it have to be a quiet environment?
Basically, quiet, not necessarily, because we filter out the speech and environmental noise. We've done tests where we introduced 100 decibel environmental noise, and we were still able to perform the measurement. Wind is another aspect, particularly turbulences in the air, which will cause arrival time variations. which would degrade the image, because then you get kind of perturbation noise in the measurements, which can maybe partially be addressed by minimizing the number of measurements that you need to do over time. But the wind is a limitation, and yeah, that would require some shielding in an outside environment, I would say. But you could just basically put some foil around it or a tent, and then you could still do it, but that requires some shielding.
Okay, so just to sort of follow on from that, so temperature as well. So if you had extreme temperature variations between repeat runs, you would get different results.
Well, basically, we do basically, as I said, we have a pitch of 3 millimeter at the moment, but we do some interleaved scanning to reduce the pitch to 1 millimeter. So we pass over the same part more or less three times.
Mm-hmm.
And then temperature could have an effect. We do have some algorithms to minimize this influence.
Mm-hmm.
And we are currently developing 3 parallel arrays to further minimize the influence of local temperature variations. But then, on the other hand, the scanning method can be fairly quick. So that minimizes the influence of temperature changes.
Mm-hmm.
But you're right, it has an effect, and it needs to be addressed properly, otherwise it degrades the image quality.
Okay, thank you.
Great. Then Eric, you had a question. Do you want to talk yourself, or you want me to read it?
Yes, no, I can do it. Can you hear me?
Yes.
Yeah.
Hi, Arno. This is Eric
Hi.
Schuur. Nice
Yeah.
talk. I really enjoyed it. So, a kind of logical question, maybe from the seismic point of view, is could you make this array two-dimensional? So you have really like a 3D wave field that you image? Or, in other words, is there a limitation to the fact that you are now using a linear array?
Basically, the housing of the MEMS sensors currently is a limiting factor. The smallest pitch that we can create is about 3 millimeter. While if you look at, let's say, spatial sampling requirements in air, then for 170 kilohertz, you would need a 1 millimeter pitch, which is currently achieved by interleaved scanning. And yeah, that's basically the limiting factor at the moment.
Yeah. So, with other words, it could be useful to go to the array, but only if you could put the elements closer together, which is now impossible. So then it doesn't pay off to do so.
Yeah. So if you would have a sensor that's small enough, you could in fact build a 2D array and perform a measurement in one go. But then, let's say, from an application perspective, you still need to mount a panel and perform an inspection, which takes time. So if the data acquisition time is in the order of minutes, that's still acceptable. Because we're talking about, let's say,
I can imagine that if you would have a full array, a spatial array, you could also do some sort of like a beam forming in the sensing side, and so you could have more freedom there in one way or another. I'm not sure how it would work out, but that's something that I could think of in a way. But because in the end of the day, the speed of the scanning is the limiting factor, of course, for the whole process. So I see that.
Yeah.
So going to a full array does not help for that scanning time, probably. It just gives you more accurate result, maybe, but not reduce scanning time.
Well, if you build more sensors in an array, then you need to calibrate them properly, which becomes more challenging compared to a linear array.
Yeah.
So the pros and cons. The interesting thing here is that basically you'd have a very low cost ultrasonic sensor for air coupled ultrasound, which is basically a point source, because let's say it's an omnidirectional receiver, which allows you to do all kinds of things that are impossible with conventional ultrasonic transducers.
Yeah, nice. No, I really like it, and so it's basically the same thing as we sometimes do with laser interferometry. When you scan a surface quickly with laser, now you do it basically with sound.
Yeah, we do have a laser vibrometer, but that's the cheapest model that you can get, which is 75K. While this sensor is 50 euro cents.
Yeah. yeah.
And practically the surface condition for a laser vibrometer is also tricky, especially for fiber panels. The surface is not perfectly smooth, and that also causes all kinds of issues where you need to average, and the data that I showed was all without averaging. We do generate a frequency chirp signal in the actuator, but that's the only, let's say, signal enhancement method that we use.
Yeah. So robust as well, basically.
Yeah.
Okay, good. Thanks a lot.
I also see that Peter raised his hand. I don't know, Peter, if you can unmute yourself or not. You can. Yes, you can.
Yeah. I think I know the answer, Arno, but can you do this underwater?
Well, a yes and no. This sensor that I showed has a small opening here, where there's the risk of water penetrating the sensor. But we have a similar sensor, which is basically in this sensor you have a membrane that vibrates under the sound pressure. And we have a similar sensor, which is same membrane with a mass added, then it becomes an accelerometer. And then in fact you can measure this underwater, and we did. The only thing is that the wavelength in water is about 5 times larger than in air.
Yeah.
Which means that there's a difference in resolution that you can achieve, but apart from that, you could use the same concept.
Okay, so I thought your answer would be, well, no, there's going to be so much kind of attenuation between the liquid to solid interface that it wouldn't, you would lose either amplitudes or high frequencies. I thought that might be your answer.
No, we did in fact did this in the water, and apart from a difference in spatial resolution, we got comparable images.
Okay, yeah, interesting.
Yeah, very nice. Arno, I have one question myself. So if other ones have even more questions, please. If you go, for instance, to slide 8, and you have this nice simulation there, I'm wondering.
It's not a simulation; it's a measurement.
Measurement. Sorry, I mean this. Yeah. I think it also moving. I don't know what was the previous of the next slide.
Yeah, here's moving.
Yeah, that's what I meant. Yeah. So you see a lot of reflections at the boundaries. Until what order of, let's say, multiple reflections do you use in here, and do they harm you, or can you use them, and these kind of things?
Well, for an isotropic material, it doesn't matter basically, because there the wavelength that you observe just depends on, in this case, the local thickness, and direction of the wave doesn't matter. As I said, we're analyzing the wave field in the wave number frequency domain. So then we just look at, let's say, essentially what's the local wavelength at a given XY location. For anisotropic media, it's slightly more challenging because then there's an ambiguity between two waves coming from different directions. They have a slightly different wavelength. And we're working on that to tackle that. But it's slightly more challenging.
I see. Yeah, very nice. I had one other question, but I think you answered this like in terms of quantifying how much better this is compared to other methods. But I mean, you gave a couple of orders, so I'm assuming there's some patent or whatever, or what you're going to do with that, I guess, right? So
yeah. We have some patent applications on this. But on the other hand, it would also be interesting to see whether this type of algorithm, for example, could be used to image, for example, the Rayleigh wave dispersion for lens seismic acquisition, to image, let's say, the near surface, because it's a different type of data processing that's normally done for seismic applications. But in this, in essence, you'd have the same type of data acquisition.
nice, interesting. All right, so if no one else has a question, I would say it was a very, very interesting talk. Also, if you look at this later at YouTube, so you just comment below the video. So if you have questions, we will reach out to Arno and ask him to comment on that. So also for all the attendees, also representing the other chapters, thank you for joining. And yeah, for me, I would then end the recording here. Jan, if you can just end it, and thank you all for coming. And yeah, and the official part is basically over.